now we will see, based on the ray diagrams we discussed earlier, now we are discussing about how the human eye works. At first, before going to directly about the explanation of that human eye, how it is working, first to see the important parts of our human eye. Okay. Now, the first one we have to discuss is about our eye lens. Our eye lens is a very sensitive and like this, very elastic, that is, okay, very sensible and elastic lens, that is, and it is like a double convex lens. So, our eye lens is a double convex lens, okay, that is a double convex lens. As it is very sensitive here, actually it is coated with two clips, clip like structure, okay, like this. Okay. These clips we call that as ciliary muscles. Ciliary muscles. Okay. So, what is the use of these ciliary muscles? Later we will discuss one by one. Okay. After this ciliary muscles, here we are having, before that, one part we have that is called as iris. We call that as iris, okay, which is acting like shutter for our cameras. Okay. Now, next one we are having, before that iris, we are having one curved surface is there like this. This we call that as cornea. Cornea. Okay. And another important part is here we are having where our images are captured, of which here we call that as retina, that is, okay, like this. So, these are the main important parts we have, our eye lens, cornea, iris, ciliary muscles and retina we have, okay. Total mainly these: convex lens, cornea, iris, ciliary muscles and retina, that is. So, now one by one we will see the importance and how they are working here. Now, one first come to the case of this convex lens. You already know that convex lens refraction there, of which it forms a real image depending on the focal length here. Actually, our eye lens can see near distances as well as far distances also. Okay. Now, if it comes to the case of ciliary muscles, how the ciliary muscles are helping here is, whenever if you are seeing the near distant objects there or far distant objects there, depending on the object distance, we have to adjust our focal length here. That work is done by our ciliary muscles. Okay. So, the role of ciliary muscles is, it is adjusting the focal length of the eye lens here, okay, adjusting the focal length of the eye lens. And next one, iris. Iris work is, actually here we are having very sensitive eye lens is present, our convex lens. That is why whenever it is exposed to high intensity light, that eye get damaged. That is why here our our iris, it is acting like a shutter here. Whenever a high intensity beam of light is entering, it does not allow all the light rays to come onto the directly to the eye lens. Okay. So, that is why whenever if a high intensity beam is coming there, then what this iris do is, it is closing the shutters there and allows only a small passes for the light rays to enter, like this. Whenever if you are exposed to very dim light, less intensity of light, then iris, what it do is, it is extending back here. So, that here the passage is more and more number of light rays they may enter inside, like this. That is the work of the iris. Okay. And another important one, the passage where the light rays are entering here, the path or the passage where the light rays are entering, that part here, this is a small hole. This part we call that as a pupil, that is called as pupil. So, pupil is nothing but it is a passage or like a hole, it is a passage for the light rays to enter onto the eye lens, that only our pupil. Okay. Now, iris actually it is adjusting the size of the pupil. Whenever it is exposed to high intensity beam, the size of the pupil is decreasing. Whenever if you are exposed to the dim light, low intensity light, the size of the pupil increases. That increasing and decreasing, it is done by our iris. Okay. And the next one we are having cornea is there. Cornea helps to focus all the light rays to come onto our retina here, to come onto our eye lens here. That is the work done by our cornea here. Okay. And after the light rays incident on the convex lens, now the light rays are going to incident on retina. Then that retina is collecting the image, okay, and sending the signals to the brain here, okay, and it is sending the signals to the brain. That is the work done by our retina here. Okay. So, these are the 5 important parts we have, that is of ciliary muscles, iris, pupil, cornea. Okay. Now, we will see how this eye lens works. Okay. Whenever if you are seeing the near distant objects and far distant objects, as I said, our ciliary muscles are adjusting the focal length of eye lens. Then how we can decide that is a far distant object or a near distant object is, our eye lens can see any of the near distant objects very clearly without straining the eyes. That distance only we call that as a near point. What is it? The near point, that is. So, near point distance actually that is equal to 25 centimeters for a average person. Okay. So, the near point is about 25, whereas near point means that is nothing but the minimum distance that our eye lens can see clearly the object, okay, without any strain, okay, without straining we are able to see the objects here, okay. That distance we call that as near point distance or near distance of distinct vision, that is, okay. So, that distance is 25 centimeters. That too, if you observe that if you are bringing the object much closer, less than this 25 centimeters, our ciliary muscles cannot adjust the focal length less here. We are having a limit for that ciliary muscles to adjust the focal length. Okay. For example, if you are taking how much is the focal length adjusted by the ciliary muscles is, as the far point, as the near point it is of 25 centimeters is there, of which the near distance. Okay. We know that our average diameter of our eyeball, which is the distance from the eye lens to the retina, that is around, we are having 2.5 centimeters, that is around 2.5 centimeters, which means nothing but our image distance screen, that is because retina is acting like a screen. That is why that distance is nothing but the image distance here, which is V is equal to 2.5 centimeters. And now we are taking the near point distance as our object distance here. So, object distance U is equal to 25 centimeters, that is. And what we need is a focal length here. How much is the focal length? Then we know that as 1 by f is equal to 1 by V minus 1 by U for our lens formula. 1 by f is equal to 1 by V minus 1 by U, then 1 by f is equal to V it is of 2.5 minus U it is of 25 centimeters. Okay. And if you apply the sign conventions, which is a very important one, so object distance is of taken negative here, whereas image distance is plus, then it becomes 1 by f is equal to 1 by 2.5, which is 25 by 10 minus 1 by 25, and minus of minus becomes plus, that is. Then it becomes 1 by f is equal to 10 by 25 plus 1 by 25, which is 1 by f is equal to 11 by 25, or you can also write that as 25 by 11, okay, which is equal to 2.27 centimeters, that is. So, this is the focal length required whenever if you are seeing the near distant objects. Okay. So, focal length required minimum is equal to how much we got? 2.27 centimeters, that is. So, whenever if you are seeing the object, if it is placed at 25 centimeters, the focal length adjusted by our ciliary muscles is 2.27 centimeters. For suppose if you are bringing the object less than this 25 centimeters, we can see the object, but the ciliary muscles are not able to adjust the focal length less than this 2.27 centimeters. So, that what happens there is we can see that image like a blur image. Okay. So, that is the problem if you are taking the object less than 25 centimeters. and at the same time we can see the far distant objects also very clearly for a normal vision there. So, which means we can see the far distant objects by adjusting the focal length again by the ciliary muscles, that is nothing but our maximum focal length. So, if you want to find that maximum focal length, then the object we are placing that at infinite distance. So, means now I am taking far distance here, of which the far point, that far point we are taking that as infinite. Near point means near distance where we can see very clearly the object without straining the eyes. Far point means now this object we can see where the object we are taking is at very far distance. Let us imagine that is infinite. So, means now the object is at far distance, infinite, okay, and image where it is forming is again on our retina, which is 2.5 centimeters, that is an average value. And we are taking now the focal length. How much is the focal length? Adjusted by our ciliary muscles. Okay. Then again the formula 1 by f is equal to 1 by v minus 1 by u. If you substitute that value, then 1 by f is equal to 1 by v, which is 2.5, minus 1 by u, which is infinite, that is. Okay. Then if you apply the sign convention, again that is of object distance is minus and image distance is plus, then 1 by f is equal to 1 by 2.5 minus 1 by infinite, that is of minus, and this is again plus. Then 1 by f is equal to 1 by 2.5 plus 1 by infinite value is 0, that is. Then finally we got 1 by f is equal to 1 by 2.5, then f is equal to 2.5 centimeters, which means whenever the object is placed at infinite distance, then the focal length here it is required is 2.5 centimeters if you want to see the object clearly. So, for a normal vision, for a clear vision, okay, always the ciliary muscles is adjusting the focal length when you are seeing a near distance 2.27 centimeters. If the object is at very far distance, it is adjusting our eye lens by 2.5 centimeters, that is the maximum focal length our ciliary muscles can adjust. Okay. This is for the case of normal vision we are observing. Okay. Minimum focal length 2.27, maximum focal length 2.5 centimeters. Okay. So, this one actually this arrangement or this adjustment of this focal length by our ciliary muscles, this we call that as accommodation of eye lens. Okay. The adjustment of focal length by the ciliary muscles to extend from 2.27 centimeters to 2.5 centimeters, that arrangement only we call that as accommodation of eye lens, that is. Okay. Now, if you see the how the ray diagram for the case of formation of image by the clear vision is. Okay. So, clear vision means we do not have any problem to see the object, whether it is placed at near distant or object distance at far distance, that is. Okay. So, for example, if you assume this is our eye lens and let us suppose this is the position of the retina we are taking at here. Now, first case I am taking as about the minimum case, means I am taking the object which is placed at here n, where n is equal to 25 centimeters I am taking. Whenever if n is equal to 25 centimeters, the focal length required here it is of 2.27 centimeters. 2.27 centimeters means that is the less focal length, that is. So, that is why here that ciliary muscles start contracting here. That is why here the size of the lens gradually increases, means the thickness increases, then our convex lens becomes a bit bulge like this. So, that the radius of curvature decreases, that is why the focal length also decreases in this case for a normal vision I am telling. Okay. Now, if object is at 25 centimeters here, now the light rays incident on our convex lens after refraction, now the light rays are going to meet exactly on the retina here like this. Okay, exactly on the retina here. This is the case if you are seeing any of the near distant object. This is for near distant object. Okay. Now, if you are taking a far distant object means object is at infinite we are taking. Okay. If object is at infinite, we already know that we have to take the light rays appears to be coming like a parallel beam of light rays. Then in this case, as the focal length required is maximum, means the ciliary muscles are extending backside here, they are going to the relaxed position here. So, that is why our eye lens becomes very thin. So, that what happens there is an increase in the focal length comes. When there is an increase in the focal length comes, immediately we can see the far distant objects very clearly. So, let us suppose this is our eye lens, and here if you are taking the object of which the light rays are coming parallel here, because object is at very far distance, that is. Then after refraction, now the light rays are going to meet again exactly on the retina here, like this. This is our retina. Okay, that is our retina here. So, this is the case we are taking for the case of minimum focal length case, and this is for the case of maximum focal length case. Okay. So, minimum focal length we have to place the object at 25 centimeters we are taking, whereas for the case of far distance we are taking object is at infinite, that is. Okay. So, we have to remember that the far point of a normal vision of a normal eye, it is about infinite, whereas the near point n for the case of normal vision, it is about 25 centimeters. And the adjustment focal length required there is, in case of ciliary muscles, that is of 2.27 is what required, and to see the far distant objects, the maximum focal length required there is 2.5 centimeters, that is. Okay. Now, we have seen how the normal eye works, how the ciliary muscles are adjusting the focal length of the eyelids. So, we have to remind those values which are that minimum focal length required to see the near distance is 2.27 centimeters, whereas far distant if you want to see maximum distance it is of 2.5 centimeters, that is. We have to remember these two values. Okay. Now, we will see the defects of the eye. Mainly we are having total 3 defects are there. Okay. So, the defects of eye, that is defects of eye. Okay. So, when you are taking the defects of eye, the first one we are taking myopia. Okay. Myopia. Myopia, another name, that is called short sightedness. Okay. Short sightedness means short, sight means vision. We can see the near distant objects very clearly, but not the far distant objects. Okay. So, now only I said if you want to see the near distant objects, the minimum focal length required there is 2.27 centimeters, that is. Now, here the problem is we can see the near distance very clearly. Short sight means near distant objects we can see very clearly. Then problem here we are getting is with far distant points. Means here if the object is at infinite, means at more distances, the problem here we are getting is the maximum focal length which is actually required there is 2.5 centimeters is there, but here our eye lenses, the ciliary muscles are not adjusting the focal length of 2.5 centimeters, that is the problem. Okay. So, have I understood the reason here? Reason for this myopia, reason is focal length is not adjusted up to 2.5 centimeters. So, that is why we are getting the problem with the far distant objects, but near we can see very clearly. So, no problem for the short sight, only problem is with the long distant objects. So, this is the problem, up to 2.5 centimeters it is not able to adjust. Okay. So, if you see the diagram here, how the light rays are there, suppose like this. If this is our eye lens, and let us suppose this is our retina, and here if you are taking the near distant one which is at the point n, there is no problem for our light rays to converge exactly onto the retina here, like this. Okay. So, this is myopia defected eye at near distant points. Okay. At near distance we are taking. Now here we are taking, if the object is at far distance, then now I am taking the object is at far distance now. Then if the object is at far distance, now the light rays are coming parallel to each other, so that here as it is not adjusting up to 2.5, always it is less than 2.5 only we have. So that is why the convergent point changes here. It is not converging at the retina, before the retina only it is converging there. Okay? Like this, before the retina only it is converging. Then problem here is because we are having less focal length there, so that is why they are converging before, and the light rays are not converging on the retina. Whenever the light rays reaching the retina, they are going like a diverging beam here. So that is why we cannot see a very clear image. Always remember, defect of eye short sight or long sight does not mean that that is of blind. Long sight or short sight means that is about we are getting a different size of objects, like a diminished or a blur image we can see. That is because of due to, as I said here, the light rays are not meeting exactly on the retina. Before only they are meeting, but when they are reaching up to the retina here, actually they are going like a diverging beam. That is the problem. So this is the defected vision. This is the defected vision. Okay. So this is the reason for this defect, myopia. Okay. Now if we come to the case of this correction part, if you want to correct this myopia, which lens to use and why to use that lens there. Okay. Now here the problem is what? Our problem is we can see the near distance clearly, but not the far distance. Means for near distance we do not have any problem, no. So which means minimum distance we can see very clearly that one. So means to that near distance we should have a limit for that. Okay. Which means here the maximum distance that myopia defected eye can see very clearly, that is our near point now. Okay. So which means that myopia defected eye, okay, can see far distance very clearly. Instead of infinite, we are having some finite value we are having. That is the problem with this myopia there. Okay. For example, let us suppose like this. If this is the eye lens and here you are having the retina and the light rays we are taking now, here this is the near point, so that no problem to this near point distance. And now let us suppose, as we can see near distance very clearly, we should have a limit for that. We are having problem with far distant objects. Far distant objects means actually for infinite, that is. The far point is not infinite for this myopia defected people. Actually you should have a fixed distance for that. Let us suppose that point is at here, f, like this. So means up to f they do not have any problem, means that maximum distance they can see without any defect is up to f. But once the object is placed after f only, we are getting the problem. Means we are taking the object at here, like this. Now what happens there is, now the light rays are coming onto the retina here, like this. After refraction, now the light rays are not converging on the retina. Before only they are converging, like this. Because we are not having the focal length 2.5 centimeters, that is. Less than 2.5 we are having that. That is why we have to change this focal length. But if you see the correction here, correction is very simple. As the object can see, okay, if it is in between f and n there. Only problem is once the object is going away after the f there, we are getting the C problem here. Okay. So that is why what we are doing for correction is, we are making the object which is placed outside f, we are bringing the object to be in between f and n. Okay. See that correction, simple, of which if it is between n and f, we can see very clearly the object, that is our short sight. Now the problem is, if the object is after f, we are getting the problem. So that is why the object which is placed after the far point, we are making the object to be in between f and n, so that we do not have any problem to see that object. If you want to get this correction, if I want to make the object which is after f, if you want to make that in between f and n, which lens I have to use is by using a concave lens, because concave lens is having a nature of formation of virtual images here. So, that is why here what happens there is, if you are using a concave lens, for example like this, if this is the convex lens we are using, of which our eye lens, and here we are taking the object which is after f like this, and before that now we are taking a concave lens there like this. Okay. Now, the light rays which are coming from the object, first it is passing through concave lens here. Okay. As the concave lens forms the image of that object which is a virtual and erect image, that too it is formed before the lens, because that is a virtual. So, that is why here the image is formed before that only here, and that too if you are able to adjust that lens here, so that here if the object which is the virtual image formed by the concave mirror, if you make that in between f and n, then we can see the object very clearly, so that the light rays are now meeting exactly on retina here like this. This is the correction part required there. Okay. So, this is the corrected vision. Okay. So, see that very simple, of which the object which is placed after f, we are making the object to be in between f and n. That is how that is possible is by using a concave lens. Okay, by using a concave lens. Then what is the use of that concave lens? Means concave lens actually forms a virtual and erect image. As it is forming a virtual and erect image, then what happens there is, the object, the image formed by this concave lens is formed in between f and n. Then what happens there is, we can see that image acting like object for our eye lens, and we can see that very clearly on the retina here. Okay. So, this is the corrected vision for myopia. Okay. Then what is the required focal length for that concave, that we have to find here. Okay. So, we already know that we do not have any problem once the object is up to f here. Let it be that distance is d. Okay. D is the distance where we can see very clearly that myopia defected eye can see very clearly. Let it be that distance is d. Then here if it is d, if you are taking, means I want to make that image, okay, where the object is at infinite far distance. I want to bring that image which is at object which is at infinite. I want to bring that image up to d, where I can see very clearly. Okay. Then what is the suggested focal length here? Okay. Then we know that 1 by f is equal to again 1 by v minus 1 by u, of which focal length 1 by f is equal to v, it is of d there, and image distance minus, we are taking that object distance as infinite, that is. If you see here, the object as well as the image both are forming on the same side only. So, that is why here both will get minus. Then 1 by f is equal to minus 1 by t plus 1 by infinite is 0, that is. Then f is equal to minus d centimeters. This is the focal. Okay. So, the suggested focal length for the corrected eye or for the defect of myopia is f is equal to minus d centimeters, that is. Okay. So, remember here the sign convention is important. Here I am taking the object to the left side of the lens, means the light rays are coming here opposite to the object distance here. So, that is why I am taking minus. And not only that, the image which is formed, that is also on the same side. That is why here I am taking even that distance also as minus here. So, that is why here the focal length we are getting is negative. Once the focal length we are getting is negative, which means that that required focal length is nothing but about a concave lens, because I got focal length is minus. So, this is the suggested focal length about myopia. Now, we seen about the myopia defected eye and how to correct the eye lens there. Okay. So, now we are coming to the next one, which is the second defect, which is called hypermetropia, which is also called long sightedness. Hypermetropia, which is also called long sightedness, that is. When you are taking this long sightedness, which means long sight, means we can see the far distances very clearly, but not the near distant objects. That is the defect with this eyesight. Okay. Now, if you are taking the ray diagram for this eye lens, which is defected with the long sight, like this. As we do not have any problem with the near distant objects we can see very clear, long sight means far distant objects we can see very clearly, problem is with near distant objects. So, the light rays which are coming from far distance we do not have any problem, but the object which is taken near here we are getting the problem. Actually, if you want to see the near distance, the minimum focal length required is 2.27 centimeters. Minimum required is 2.27 centimeters, of which we already derived that value. But here, as the eye lens is not able to adjust to contract up to that 2.27 centimeters, which is always more than this 2.27 centimeters, then what happens there is, because of due to having more focal length, then converging point is also at a long distance we have, which means the image is not forming on the retina. After the retina, the image is forming here like this, because the focal length is actually required is less 2.27, but it is not making up to 2.27, it is always more than 2.27. That is why the converging point is after the retina we have. So, that is why when the light rays just before reaching the retina, that is no more like a converging point. So, that is why you are getting a blur image here. This is the defect of a hypermetropia. Okay? Which means actually we have to see the near distant objects up to the 25 centimeters very clearly the object. But the problem here is we are not able to see that 25 centimeters here, which means there is a change in the near point for the case of this hypermetropia, of which that near point shifts to, let it be, that is here n dash. Okay. Actually at here at 25 centimeters, but it is not able to see the near distance, means that is of the near point is shifted to more distance here. Okay. That point only we call that as a near point of hypermetropia. Near point definition is here, that is the minimum distance that hypermetropia defected eye can see, that only we call that as near point here. The minimum distance that hypermetropia defected eye can see very clearly, that only we call that as near point, of which in our case here n dash is the near point. So, observe that clearly here, if the object is after n dash we do not have any problem. Problem is coming if the object is after n dash. Okay, means we cannot see the near distant objects clearly, only problem is with the far distant objects. So, that is why what we are doing is we are making the object which is placed in between n and n dash, we are making the object to be after n dash, that is possible only by using a convex lens. Now, let us see how to correct that. If you are taking a convex lens before our eye lens, here like this. Now, this is the original near point, but this is the near point actually for the case of our eye lens. Now, we are taking the object which is in between n and n dash. Now, what happens there is, here we are having one extra convex lens is there, and convex lens actually its nature is converging nature. So, that is why here what happens there is that light ray is converging 2 times here like this. Then finally, the image is formed exactly on retina here like this, which means these light rays are appears to be coming from more distance here like this. This is going to be the object position. Original position is here, but finally the object position appears to be at O dash at here, that is. Okay. So, this is the correction for hypermetropia, that is. Okay. This is the corrected vision of hypermetropia. Okay. So, very simple, only one thing, we can see the object if it is after n dash. Problem is coming only if the object is in between n and n dash. So, that is why we are making an object which is in between n and n dash. We are making the object to be after n dash by using a convex lens. Okay? That is the correction for hypermetropia. But what is the focal length required for that convex lens? That we are seeing now. So, means suggested focal length for hypermetropia. Okay. So, let us suppose this n dash, which is the near point, let it be that is of d. D is the near point distance, that is. Then we already have the object here we are taking. Okay. So, where we want to place that? Exactly after that d here. Okay. So, the image here, object is at 25 centimeters actually, and we want that image to be at d position there. Okay. At d means our near point, that is. Okay. Then we need the focal length f. Then again, as 1 by f is equal to 1 by v minus 1 by u, then 1 by f is v it is of d and u it is of 25, that is. Then again, if you apply the sign convention, so in this case object and image both are on the same side here. So, that is why we have to take both cases minus, that is. Okay. Then 1 by f is equal to minus 1 by d, minus of minus becomes plus 1 by 25, that is. If you take the LCM, then 1 by f is equal to 25d, okay, and of minus 25 plus d, that is. Then 1 by f is d minus 25 by 25d, that is. Then finally f becomes 25d by d minus 25. This is the correction required. Actually, if you observe, d is more, 25 is less, d is up to n. Sorry, n is up to 25 means up to n, d means more than 25, that is. So, d minus 25 value is positive. So, that is why here f is positive. If f is positive means the required focal length is a convex lens. In that way, we can decide that the suggested focal length for this hypermetropia is f is equal to 25d by d minus 25. And another one is hypermetropia, which is of long side. For myopia, suggested focal length for myopia, we got minus d, that is. Whereas, in case of hypermetropia, we got suggested focal length is 25d by d minus 25, that is. Okay. Now, another defect we have, that is called as presbyopia, that is. Presbyopia actually it comes because of due to for a long time if the ciliary muscles are working, then we are getting this problem of presbyopia, that is, of which most of the cases we will see that in old people, that is, because that is coming because of due to aging, that is. For a long time as the ciliary muscles are working here, they are going to be to a relaxed position here. So, that is why they are not able to converge these light rays onto the retina. Okay. So, the correction for the presbyopia required is we have to use a biconvex lens, just like we use in case of hypermetropia here. Okay. Just like the case of hypermetropia, because those are in the relaxed position means focal length is more for them, they cannot contract much. As they are not able to contract much here, that is why here the focal length required is less. So, that is why we have to use a convex lens here for the case of presbyopia, that is. For the case of numericals here, we already know that formula for power of lens is 1 by f, the reciprocal of the focal length. Okay. Power of the lens is equal to 1 by f, that is reciprocal of the focal length. Then for the case of myopia, the required power is p is equal to, this is for myopia. Okay, required focal length is 1 by f, where suggested focal length it is of 1 by d is minus d, that is. Okay, so minus 1 by d, that is. And whereas hypermetropia, if you take for hypermetropia, again that is of 1 by f, that is 1 by it is given as 25 d by d minus 25 that is. So, finally, we got d minus 25 by 25 d. That is the power required, the power of the lens required to correct myopia and to correct hypermetropia. Okay. Then, how to use this while solving the numericals, that we will see that. For example, a person is defected with myopia, having myopia short sight there, and we know that his far point distance, that is of d value, is given as 25 centimeters that is. Okay. Let us suppose 30 centimeters. Okay. Then this is about myopia defected vision. Then the focal length suggested focal length is minus d centimeters that is. Then it is equal to minus 30 centimeters that is. As it is about myopia here, the power required, power of the lens, power of the lens is equal to 1 by d, that is of minus 1 by 30 that is, but this is in centimeters. Okay. So, we have to convert that into meters. Meters means 100 we have to take. Then it becomes 3 get cancelled, minus 3.33 d we will get, where d means diopter that is. Okay. So, power units is diopter. This f we are taking in meters. Okay. Then power of the lens, its units are diopters that is, or reciprocal of meters that is. Okay. 1 by meters. So, that is why here we got minus 3.33 d that is. Okay. Because here we have to use a concave lens. So, that is why we got minus 3.33 d that is. Okay. For suppose if they are having the doctor's prescription, if you are having the focal length required there or the power required there, if it is given as p is equal to minus 4 d, what do you mean by that is the power which is equal to 1 by f is equal to minus 4 is there, then f is equal to minus 1 by 4. Minus 1 by 4 means minus 0.25 into, actually it is of meters that is 0.25 meters, or you can also write that as minus 25 centimeters that is. Okay. So, that minus represents we are using a concave lens that is, and here the far point distance which is the suggested focal length, that d value that is, because f is equal to d. As f is equal to d, then f value we got 25 centimeters that is. Okay. So, in that way, if a power of the lens given, we can find the far distant point also for the defected eye, where f is equal to minus 25 means that a distance is equal to 25 centimeters, like this. This is for the case of myopia. Okay. Now, if you are taking for the case of a hypermetropia, how to solve a numerical is, we know that for hypermetropia that required focal length is 25 d by d minus 25 that is. So, that is why let us suppose that myopia defected vision problem we are taking. Okay. For example, if the near point we are taking, near point for the defected eye is equal to 40 centimeters that is. Okay. So, which means our near point distance d is equal to 40 centimeters. This is for long sight we are taking. Okay. So, d is equal to 40 centimeters that is, then we know that formula f is equal to suggested focal length 25 d by d minus 25 that is, then 25 into 40 by 40 minus 25 that is, then 25 into 40 by 40 minus 25 which is 15. Okay. So, 5 3s here and 5 5s which is of 200 by 3 that is. Okay. So, 200 by 3 which is of here f is equal to 200 by 3 we got. Then this is f value, then we have to find, and that too this is of centimeters that is. Then we need power, power is equal to 1 by f that is, which means 1 by 200 by 3 and this is in centimeters, means we have to convert that into meters, which is into 100 we have to take. That 100 get cancelled and 3 come to the numerator, it becomes 3 by 2, which is 1.5 that is. And if you observe here that the power we are getting is plus 1.5. If it is plus 1.5, as the power is plus 1.5, which means this represents we are using a convex lens, okay, and the power given there is 1.5 D that is. Okay, the power suggested for that is 1.5 D that is. Okay, like that we can solve this numericals there in case of myopia and hypermetropia. Now, as we already seen about how to do the numerical for the case of this myopia and hypermetropia there. Okay. Now, another important one about the power is when you are using two lenses at the same time, then the power formula is given by, let us suppose if you are having a convex lens with focal length f1, let us suppose you are taking another convex lens which is of focal length f2. Okay. This one having the power p1, this one having the power p2. In this case, the formula required, the final focal length f is equal to of which 1 by f is equal to 1 by f1 plus 1 by f2, that is the resultant focal length we are getting. And at the same time we know that 1 by f1 is nothing but p1 the power, and 1 by f2 is nothing but p2 that is. Then this is the final power. If the distance between the two lens is 0, then we are using this formula. If there is a distance is present between both the lens, this is one convex lens, this is another convex lens with focal length f1 and f2, and let it be this is p1 and p2, and let us suppose the distance between them is d, then the formula is given by 1 by f is equal to 1 by f1 plus 1 by f2 minus d by f1 f2, that is, then 1 by f which is p is equal to 1 by f1 is p1, 1 by f2 is p2 minus of d 1 by f1 p1, 1 by f2 is p2, that is, and finally we got p is equal to p1 plus p2 minus d p1 p2. This is the case we are using if there is a distance is present between the two convex lens we are using. The same formula we have to apply even for the case of concave lens also, but we have to use for any of the focal lengths here, we have to apply the sign convention here. Okay. Now, we will see about the refraction of light through a glass prism. Okay. Prism means you already know that prism we are having total 2 triangular surfaces and 3 rectangular surfaces, that is. Okay. Now, we are seeing a monochromatic light. Mono means single, chromatic means color or wavelength, that is a monochromatic light. Okay. Mono means single, chromatic means color or wavelength. Okay. So, a single colored wavelength we are taking here. Okay. Now, this monochromatic light, for suppose if it incident on the glass prism, from the front side if you see only the triangle surface we can see here like this. Let us suppose this is A, B, C is a prism. AB is one rectangular surface, BC is the base another rectangular surface, and AC is also another rectangular surface, that is. Now, let us suppose a light ray incident on the AB surface here like this. Okay. To this surface, now we are having a normal here like this. This is the normal N1, that is. Okay. Remember, we are taking the light ray, incident light ray is from air. This is our incident ray. Okay. Now, whenever the incident ray you are taking, that is in the air medium, that is. Now, here glass, this is our glass prism is a glass which is a denser medium, that is. This is glass which is a denser medium, that is. So, as this is a denser medium and the light ray is coming from rarer to denser, then the light ray bends towards the normal. The actual path of the light ray is actually it is going straight there like this, but here the light ray bends towards the normal here. So, it is bending towards the normal like this. Okay. Now, the refracted ray which is making an angle, let it be that is of angle of incidence is I, angle of refraction is R1. Now, the light ray is incidenting on the second surface here which is of AC surface. Now we are having another normal we are getting. So for this surface of AC, let it be, this is the normal, okay, which is normal N2, that is. Now the light ray here, as it is coming from glass back to the air, okay. Now the light ray bends away from the normal, because this is from denser to rarer medium. So that's why here the light ray bends away from the normal here, like this the light ray bends here. The light ray which is coming outside finally, that you call that as emergent ray. This is called as emergent ray, that is. Okay. So normal N1 we got, normal N2 we got, and angle of incidence is there, angle of refraction, let it be, this is R2, which is the second case angle of incidence, and finally the emergent ray making an angle with the normal, let it be, that is angle of emergence E, that is. Okay. And the angle between the two refracting surfaces, which is between AB and AC, that only we call that as angle of the prism A, that is angle of the prism. Okay. Then how much is the light ray deviating from its original path, that only we call that as angle of deviation, that is. So here this is the angle of deviation D. Okay. So total we got 4 angles are there: angle of incidence, angle of emergence, angle of the prism, and angle of deviation, which is inside. Okay. Then if you take a relation between these 4 angles, we will get angle of incidence plus angle of emergence is equal to angle of the prism plus angle of deviation, that is, this is the relation between the 4 angles. I plus E is equal to A plus D. But remember, whenever if you are taking the angle of incidence, okay, then if you are increasing the angle of incidence, gradually the angle of emergence decreases here, angle of emergence decreases. At one particular stage, the angle of incidence and angle of emergence both are equal, and the deviation made by that, actually here it is minimum deviation here. Okay. So the deviation angle is minimum. Okay. So when you are increasing the angle of incidence, angle of deviation gradually decreases. At one particular stage, angle of incidence is equal to angle of emergence. That point only we call that as a minimum deviation point. That is called it as minimum deviation point. Remember, whenever angle of incidence equal to angle of emergence, minimum deviation point, the light ray which is coming from this point to this point, the inside refracted ray and BC, both the base, these two are parallel to each other. Okay. Those two are parallel to each other. Then we can say the light ray is deviating minimum, that is. Okay. Then if you want to find the refractive index of this glass prism, then that formula is given by mu is equal to sine of A plus dm by 2 by sine A by 2, that is. Okay. Mu is equal to sine of A plus dm by 2 by sine A by 2, that is. Whereas A is angle of the prism, mu means refractive index of glass prism, and A means angle of the prism, and here dm means minimum deviation, that is. We are taking that as minimum deviation. This comes when angle of incidence equal to angle of emergence there. Okay. This is the formula to find the refractive index of the glass prism. Okay. So, by using this angle of minimum deviation. Now, we will see the polychromatic light refraction through glass prism. This one is monochromatic light when passed through the glass prism. Now, we are seeing polychromatic light. Polychromatic light. Whereas poly means more than one, which is more than one. Okay. And again chromatic means wavelength, that is, or the color. So now we are taking here the light ray which is having more than one wavelength here. Okay. Best example for that is white light you can take. Okay. White light. So polychromatic light is a white light is a polychromatic light having more than one, because it is having 7 different colors. Now we are seeing the refraction through this polychromatic light through a glass prism. Okay. Now let us suppose this is the glass prism. Now you are taking a white light which incident on this glass prism. Then after refraction, what happens there is, as these are having, white light is having a 7 different colors and each color having its own wavelength is present. But once the refraction takes place, if the light ray is going from one medium to another medium, as we already know that during refraction there is a change of velocity is there. As all are having 7 different colors with different velocities, okay, there is a change in velocity is present for the 7 colors here. That change in velocity is different for different velocities. Okay. So there is a change in velocity is there for different colors in a different way. So that's why here the light rays are not going no more in the same line, all are taking their own path. This only we call that as splitting. Okay. The splitting of white light into 7 different colors, that only we call that as dispersion phenomenon. This only we call that as dispersion of light or dispersion of white light. Dispersion of white light. This is what we observe even in case of our rainbow also. Whenever the sun light rays are coming on a rainy season here during rain, what happens there is that water bubbles, they are acting like here our glass prism. After refracting through that, we are having total internal reflection takes place. Again, that is also a special case of refraction here. There is a splitting of white light into 7 different colors, that only appears to be like a rainbow here. Okay. So remember, in this case of refraction through glass prism, okay, the more deviated part, more deviated light ray is violet and minimum it is of red color, that is. Okay. So least deviated ray is violet, least deviated ray is red color and maximum deviated light ray is violet. Okay. Because here the red color light is having maximum wavelength is present, whereas in case of violet it is having minimum wavelength, that is. Okay. See here, as the refractive index we already know that is related to the velocity here, of which mu is equal to c by v. Mu is equal to refractive index, mu is equal to c by v, where c is the speed of light in the vacuum and v is velocity of the light in the given medium we are taking. Okay. So the refractive index mu is inversely proportional to the velocity here. Okay. See, velocity is more, velocity of light is more for red color. That is why it is used as the danger symbol also, red in color. Okay, like we see in the traffic signals, that is of red in color, that is. And the minimum wavelength it is meant for velocity of light is minimum or less for violet. Okay, in case of violet it is minimum. As the red color is light is having more wavelength, more velocity is there, it is having more wavelength also, because we know that v is equal to n lambda, then v is directly proportional to lambda, which means velocity of red color is more than violet, is more than violet. Then its wavelength is also more for the case of red color here. As velocity is more, then wavelength is also more. But velocity and refractive index both are inversely proportional to each other. That is why the refractive index of the red color, actually it is less when compared to the refractive index of violet. This refractive index and deviation, okay, both are related directly proportional to each other. When you are having more refractive index, the deviation it is of less. If the refractive index is more, then the deviation is also more we have. So that is why here the deviation angle for red color is less when compared to the deviation angle for violet color. These are the relations, very important one. Okay. So red color velocity is more, so that is why here we are having more wavelength is present. As there is a more wavelength is present, we are having more refractive index is present. As we are having more refractive index is there, then here in the case of that deviation is more for violet. Whereas in case of red, as the refractive index is less, that is why the deviation for the red color is also less. That is why while coming out from the glass prism, here the red color light is having less deviation, which comes first. This is the screen. Okay, which comes first, and last we are getting is violet. This is the order. Okay, so violet to red, that is.